Welcome everyone to this new episode of Among Us, Human-Robot Teaming. Today is an exceptional episode. As you can see here, this is the ICRA logo this year. The ICRA conference is the premier conference on robotics and automation, sponsored by IEEE. And today is going to be an exceptional episode because we will first go and visit the exposition hall, where you will see many new robots and prototypes that are reaching the market today, with several expositors from all over the world. And later, we will have a poster session. We will go to the poster session where our research group is presenting a new work, a recent work on neuromorphic cameras, event-based cameras. This work is co-authored by two of my PhD fellows, Hamza Zafar as a first author, and Kumayl Moosavi, and myself. Later, we will have a nice chat with some representative from the Italian Institute of Technology, IIT, which are developing a very interesting motion capture system, which works without markers. And later we will have a chat with Erik Ballesteros, which is an MIT PhD fellow, which is working on a very cool concept, augmenting people with extra limbs, extra arms, extra fingers, maybe a tail, like a superhero. Later we will also talk with Kentaro Barhait, which is also a PhD fellow at the MIT Institute. He's working with a really cool concept of building this full closure grasping device. And at the end, we will have a nice talk with Francesco Ferro, who is the current president of EU Robotics and also the CEO of Pole Robotics. So we are going to look at the vision of EU Robotics and how this technology and these ideas are connecting all together. If you are watching this on YouTube, I invite you to follow this timeline as I described. If you are watching this on our podcast channels, then I will like to invite you to possibly skip to the next sessions, since the first session is going to be a tour around the exhibition hall. So enjoy this episode, and remember that we are among us, they are among us, human-robot teaming. Welcome everyone. We are at the exposition hall at ICRA 2026 in Vienna. It's the biggest robotics and automation conference sponsored by IEEE. And here is a lot of robots that I would like to show you. Follow me. So here we have some humanoids playing football. As you can see, they are cute and nice, and people are just interacting with them. As you can see, there are different booths from different companies. This one is Booster, and we can just go around and see the other booths. It's a huge hall with many exposition. Here we have some more humanoids. These are a little bit bigger and more articulated. And as you can see there is a humanoid making popcorn. So we can continue our tour. Here there is an interesting demo with a humanoid playing cards. As you can see, the robot is actually able to shuffle cards and pick up cards. So it it looks like the robot has a very good dexterous ability. And the people are still they're interacting and playing like in a casino. Okay, we can continue our tour. We have here we have some manipulators with grippers from the shadow robot. So we have like universal robots manipulators with grippers that are designed by the shadow robots company. Some more small, cute humanoids. And here we have more humanoid robots and quadruped robots. For quadruped robots, I think the market is very competitive now. There are many alternatives. So even the market about humanoid robots is expanding very rapidly, and we start to have many alternatives as well. Here is the booth from Unit 3, and we can see several new models. So this is a G1 that we have recently acquired in our lab, and several other robots. As you can see, the G1 is quite agile and it's dancing around different quadrupeds. And we can continue our tour. So some more humanoid robots with a robot that is sketching on a sketchbook. And we also have some interesting designs, like robots that do not really appear like they're not like humanoid, but they still have hands and arms. Different manipulators and robotic hands. And what is interesting now, we are transitioning to the area that is dedicated to the challenges. So challenges are like competitions where different teams of researchers compete with each other within specific thematics, like grasping or maybe locomotion. So we can have a quick look of this area. So actually this one is the team from Vienna, and I'm very much connected to them because I was studying in Siena, and I would like to, so they are now focused on their challenge. This is my colleague Jonathan. I'm just showing off what you're doing here. It's a challenge, right?
Yes. It's the Endover challenge, where basically you have a system with cameras that detects the position of the end of one person that is passing a glass or other boxes and other stuff to the robot, and the robot has to grasp it and leave on the table. And actually, the very nice thing is that we knew the objects just this morning when the challenge started. So everything is trained with other objects, and now we have to see how the system can generalize over brand new objects. So we have a box with, so we train mainly on glasses, but today we have transparent bags with
some candies.
Candies and very other things. So it's
I
nice.
see that the team is very focused and
Yeah. We are running because we have to prepare the setup and everything. So
best of
Tough.
luck.
thank you.
Buona fortuna. Ciao. So we can continue our tour. You see the other teams are again focusing on the same challenge. The configuration is similar. Each team has a robotic arm and a gripper, and they are going to do this end-over challenge. So end-over is very related to the concept of human-robot teaming, because end-over means that the human is going to pass an object to the robot, and the robot is going to grasp it. So this very close collaboration. So as you can see, it's several teams competing. Guys, we are making a small podcast, and we would like to ask you, which team are you representing?
We are part of the Broken Arm team, and we are participating in the RGMC challenge, which is a human robot handover track.
Nice.
And yeah, we're currently finishing up our competition. We have 2 more configurations left to go.
Great.
And then we'll see how we
Are you
perform.
happy with the result?
Mixed.
Mixed.
Some things worked very well, others were a bit challenging, like the bags. Like we couldn't fully grasp them, and that's why we
The
unfortunately
plastic bag, right?
Yeah, like it's way too squishy.
Too squishy.
But apart from that, the others went well.
Great. I think that your team seems to be very motivated.
Yes.
Best of
Definitely.
luck.
Thank you.
We can continue our tour to see the other challenges. So as you can see, this scenario here, this environment has been built specifically for mobile robots to challenge with each other. So it's like a track they have to follow. We can go ahead and see a little bit closer. So you can see the mobile robots running around. Some of these tasks are obviously autonomous tasks, and the challenge is that the teams need to adapt to the regulations of the competition, and they have to do their work here right now. Actually, you can see that there are different desks where the team is updating and programming their own platform. So as you can see, like this is like behind the scene of the competition. Hi guys, can I disturb you? We are making a small podcast.
Or kind of in a rush, maybe some.
You are in a rush.
Yeah.
Some pressure on the competition.
Oh yeah, because we only have 2 hours to do the whole map and tune our algorithms. So we're going super slow and not that stable, but at least we're driving.
That's good.
And
I will not take your time. Just which team are you representing?
Vol 1 from Université Laval, Canada.
Great.
Thank
Best
you.
of luck.
Yeah, thank you.
So as you can see, the teams are under pressure and they are very competitive. So we will just continue look around. You can see for some of them the screen with the ROS and the gazebo, the robotic operating system. Most of them are using the same system. Here you can see the platform that they are using. Basically a mobile platform with wheels. And you can see some of the sensors. There might be a LiDAR. There might be some other sensors that they use for navigating. But basically to do SLAM, simultaneous localization and mapping. As you can see, there are several competitions. This, for example, is competition number 7, and it's about physical competition, obstacle course, and so on. Like, there is a specific maze that has been built with boxes, and this is like the terrain where the robots have to operate. And then some of the manufacturers actually organize the challenges. Like, for example, this is from Agibot. The point is that each team gets to use the exact same robot, so it's fair for everyone. And the company normally will provide the robot for the teams, and they can compete here in this challenge. So as you can see, there are different boxes, different setups, and this is the Agibot World Challenge 2026. Like, for example, here we have an interesting setup where the robot is supposed to pick up items from the supermarket grocery shelves and place them into a shopping cart. As you can see, there are several products that were supposed to be picked up just and deployed into the shopping cart. We can just continue the tour. So it's really huge. Like, you see, there are so many different competitions going on, and the teams are currently working with their systems. Here we see some more humanoids. And this is very interesting challenge where there is an environment that is built with different steps and different ramps. So it's quite challenging for the robots to operate in this environment. It could be very similar, for example, to the scenario of search and rescue operations, where you have different buildings that have collapsed and terrains that are really difficult to navigate. And then the robot sometimes is required to do some specific manipulation tasks, like opening and close valves, pushing buttons, remove objects or grasp objects, open the door. As you can see there is a door that the robot is supposed to open or close. So this is specifically designed for humanoid. So as you can see, there are like handles and key to be open or closed. And then, as you can see here, the terrain is really difficult to navigate. So the robot is supposed to be able to, locomote across different obstacles and jump out. And as you can see, there is a quadruped now operating in the terrain there. Can get closer. So as you can see, it's very difficult for the robot to navigate in this kind of terrain. So at the moment, the robot is operated. As you can see, there is an operator with a joystick, and the cable is just for safety. Yeah, so then you got the idea of this challenge. We can continue the tour. Here there is another company designing humanoid robots. So as you can see, there are really many competitors now in the market. Here we have some other interesting designs for a mobile robot that combines wheels and legs. Some other humanoid robots. Now the robot is waving at us. Fully autonomous, heavy-duty humanoid. And as you can see there, it's also performing a task, taking an object from a grocery shelf. So it's just deploying the object here. Some of these companies are collaborating with NVIDIA. Okay, we can continue our tour. Yeah. Here is a robot, a humanoid robot playing chess or other table games. Some other humanoid robots. It's different designs. This is with the wheels, not legs.
You guys are interested? Yeah.
Then we are approaching the booth from Pole Robotics. So they also have a humanoid that is also interesting from a design perspective. It doesn't have a head, and the actuation system for the legs are made with linear actuators. So this robot can walk and jump. Here we have some service robots. And I think that now they are showing a demo with teleoperation. As you can see, human and machine. The human is driving the machine and grasping an object on the other side. So again, an example of human to robot teaming. Interesting to see like the development of different hands. Now most of them are sensorized, so you can assess the torque that they are executing while grasping. Here we can see some more quadruped robots, also combining wheels and legs. And actually, it's a modular design. The quadruped robot is split into 2 modules now, and the configuration is similar to like a Segway. So from 4 legs to 2 legs. And now the robot is going to climb the stairs. And then there is a ramp down, and probably now it's going to connect back to the other module. As you can see, the docking. They are docking to each other. So they go down and they get closer. And they connect together. So now it's a quadruped robot again. So now 2 robots have made 1 robot. So this is also an example of collaboration between robots. And possibility to switch from 4 legs configuration to 2 legs configuration. Let's see how it handles the stairs and down to the ramp. Nice. Here we have a torso robot grasping some objects. As you can see, this is like an example of performing daily tasks, like washing dishes. Okay? So there is really many manufacturers exposing and showing up their products, and it's really nice to see that now some of the robots that just a few years ago were just research products are actually reaching out the market, and we really look forward to see these robots coming and reaching really the people in everyday life. Okay, today we are at ICRA, the premier conference for robotics and automation, IEEE ICRA conference, and we are in Vienna, in Austria. It's been a very nice experience for us to be here, and Kumayl, one of my PhD fellow, is presenting a poster. This poster is about event-based cameras, which for us working on human-robot teaming is one of the key sensors that we are exploring.
Yeah.
And so human-robot teaming is the concept that starts from as an evolution from robots that were initially trapped in a cage, like animals, wild animals, and then they were at some point liberated. And in the literature, we can see the progress into human-robot interaction first, and then human-robot collaboration. And the gap between humans and machines becomes smaller and closer.
Yeah.
So then physical human-robot collaboration, when they finally, machines and humans touch with each other.
Mm.
And today we're working on this concept of human-robot teaming, where humans and machines share space, forces, and intention. And when this kind of close teaming happens, it's very important to have very high awareness of the environment. So we use sensors everywhere. We use sensors on board of the robots, as we used to do before, sensors in the environment, and also sensors on board of the humans. So event-based cameras could be placed everywhere. They could be placed on the robot, they could be placed in the environment,
yeah,
and they could be placed on the human. So, and today, Kumayl is presenting this paper titled Neuromorphic Event-Based, Event Camera-Based Object Recognition and Grasping Position Detection using a transfer learning enhanced multitask model, which is authored by Hamza, Zafar as the first author, Kumayl, and myself. And I'd like to show you the poster itself first. Kumayl and the team decided to make it very graphical, so very little text. So Kumayl, would you like to tell us a little bit more about this work?
Yeah. First of all, there are two data sets that we use, which is the event graph and the neuromorphic, the neurograph data set. Now, what these data sets are, these are different objects and their grasping points. So the event graph data set has 97 objects and their single grasping points. So we have their IDs, what type of object, and where is the grasping. Now let's talk about the neurograph data set. And in that data set, we have 157 objects and multiple graphs. So it can have a lot of different positions that can be grasped from for a robotic manipulation.
So basically, the idea for the people that are not within this field, we are using a special camera that is different from RGB cameras, from traditional cameras.
Event camera, traditional RGB cameras, what we get is a very high exposure of data. So first of all, we have motion blur. We have very low frame rate. Low frame rate in the sense that RGBs can go up to 60 frames per second with maps. But if we go with event cameras, there's less motion blur. We have only sparse data to deal with, and we can go up to 10,000 frames per second.
And the event camera doesn't capture the entire frame, but
it only
only
event camera, it only captures change in the scene.
change in the scene.
It does not capture anything else.
That's why it's also privacy preserving.
Very privacy preserving as well, and because of that, it only captures data which is changing. It takes less energy for the sensor itself to produce this.
So low energy, privacy preserving, very good for from a computational perspective.
Exactly. And the best part is it's asynchronous. So
It's asynchronous.
still works asynchronously. So that's why it is far better in terms of capturing these images as compared to RGB camera.
And you want to use
the event camera.
you want to use this camera. We want to use this camera for robotic grasping.
Yeah.
Right.
Yeah.
So grasping with a manipulator, grasping an object with a manipulator.
Yeah, exactly. So what we did here was we created we first used these event streams because event data comes in streams. So we accumulated 30 milliseconds windows and we created frames out of those event streams because conventional deep learning models, they need to use convolutions and we need frames for that. So we convert these events to frames, and then we created a channel sharpening attention based adaptive inception network. Now what we do here is we are doing a multitask model in which we are detecting what the object is and where is the graph. So first we trained it on event graph dataset. We trained it and we got good results for classification up to 99.5% accuracy and 93.7 IOU data for grasping. Basically, it's an object detection of the class. Then what we did was we transferred the learned layers of the event graph to neurograph dataset. So we have already a trained layer of all of these supposed model that we did.
The pipeline that you have.
Exactly. We shared the model layers to this pipeline and we trained neurograph again.
So that's very important because you are transferring the learning. It's generalizing.
We're trying to generalize, and the part is event graph. It has only 97 objects and single graph.
Nice.
Graph, it has a lot of more objects. It's 157 objects and multiple graphs. So it's a far harder data set.
Much harder.
Harder. So we trained it on this, and if we see our results, without transfer learning, don't get very high accuracy or IOU results. But when we did transfer learning with eGraph, we get far better results with neurograph.
Nice.
So and we use event camera for it.
So it means that the model is able to generalize from a small limited data set
to a larger, more difficult data set. Yeah, exactly. That is the whole contribution that we did.
Very nice. And what about the comparison between multitask and single task?
Yeah. So we also did a comparison in because our model was multitask. in which we did classification and regression together. So what we did was we also created a single task comparison in which we removed one of the heads for each case, and we tried to see if without regression, does classification get better, or without classification head, does regression get better? But when we see the results, we see that it is not far different, because in multitask we get 99.47, but with only object recognition we are getting 99.68. It's not a big
So, but
improvement, but
even though you isolate,
we isolate the heads, we are still getting the same level of business.
very good. So I think that this is very interesting work. And have you got any comments from, it's a huge hall,
It's all
8,000 participants.
come, but people who are interested in event camera are coming to my booth area.
So today when I was looking for our poster, I entered the room.
It was a big hall.
It was a big surprise, yeah. And so first, I think we should also thank Hamza for leading
Yes.
this work.
Our main author is Hamza Zafar, and he has been leading this work, and he has been leading a lot of different works with event cameras. So please connect with him as well if you want to learn more about event cameras and work in future research with event cameras.
So what's next?
So right now we have created our own database setup, and we are doing we are creating data sets with humanoids and robot dogs with event cameras, and we are trying to detect the human intent, human position, and human where the human is basically walking in different scenarios, in industrial scenarios, in home nursing scenarios, and we are creating data sets and models to detect those humans for those robots.
So basically what we want to do is, since we have this teaming concept between humans and machines, we want to be proactive, right? We want to be aware of what is happening and where the people are heading, so that we can adapt the machines according to the scenario dynamically.
Yeah.
And I think that is very, very promising. And one last thing is, I know that you guys have been able to run the model into Raspberry Pi.
Yeah.
So instead of having a cloud computing distributed,
our complete event camera database setup is all incorporated in a single Raspberry Pi
locally, no internet needed.
No, nothing at all, and we have a battery power bank inside our system that we have created, and we can go up to 60 FPS with the spatial and temporal alignment of event camera and RGB data as well for the database setup.
So we are talking
So it's very portable setup.
1,000 times reduced in size, the model.
Yeah.
Thank you, Kumayl. Then
Thank you so much. Thank you.
looking forward to the next future work.
Yes.
Okay, we are back at ICRA 2026 in Vienna. Very nice venue and a lot of people. And I have the honor to be here with Pietro Balatti from the Italian Institute of Technology.
Yeah, nice to meet you.
Very nice to thank you for having me in your booth here. I was really immediately attracted by your setup. And I would like to summarize to our listeners the concept of human-robot teaming.
Yes.
Which is this new paradigm of sharing between humans and machines, sharing space, like a physical space, a physical environment, sharing forces, maybe lifting a heavy object together, and sharing decisions. And I think that your setup here is within this scope.
Yeah, sure. So it's very important in human-robot collaboration that the robot is aware and knows exactly where the human is doing and where is doing what. So at IIT, we started building a motion capture system that is based only on cameras, and it's completely markerless. So you don't need to wear anything, and the system is able to track exactly your body posture, the position of every joint of your body. So in this case, we are transferring the knowledge to the robot, and the robot knows exactly where to go and where not to go, especially not to make damage to the environment, or especially not to hurt the human. So it's quite crucial in human-robot collaboration when there is a lot of interaction between the robot and the human that come close together for the robot to know exactly where is the human.
You use the right word, sharing knowledge.
Exactly.
And it's out of curiosity in the podcast, we have a song at the end of each episode
Great.
that actually use this word, sharing knowledge, sharing autonomy.
Oh, it perfectly fits.
It fits perfectly with the theme of the podcast. And
Yes,
I'm
can show
curious
you.
about, so
Yeah,
we
yeah.
have different cameras.
Exactly. So basically, our system is camera agnostic. It means that you can use any camera, any RGB camera. You don't need depth. But the magic happens inside this box that we call it the smart camera. So all the computation and our powerful GPUs are inside here, and every webcam has its own smart camera. So that it means that we don't have any bottleneck. You can
It's a modular design.
Yeah, exactly. You can put as many nodes as you wish, so we can cover even a much larger area. And in this case, I can also show you the demo.
Does it require a calibration process?
Yes, but it's very fast. As you can see, we have the cameras that are attached to poles. You can move the camera in a new room. You just place the cameras to point to the area you're interested in. And then the calibration requires less than 1 minute. So we have a sort of probe. It's like QR codes you show to all the cameras. And then you put them on the ground to fix the ground, to know, so that the robot
reference.
knows the reference system. Okay. So if you come back with me to the background, you can see that after 2 or 3 seconds, we appear on the screen. Our skeleton appears. So as you can see, I'm the green avatar. You have the red
I'm
one.
the red.
You see, this happens seamlessly. So we are not wearing any marker. It's just the cameras, our AI proprietary algorithms, and the magic happens in real time.
Very nice.
So we are able to track the body posture, but also we are able to track objects. So this is a spray, normal spray. As you can see, I'm having it. Okay, I can pass it to you. You can see tracking in 6 dimensions. So we have both position and orientation. And as you can see, it's pretty accurate.
So it can be any object, or you need to...
The objects in our dictionary, but you can add easily any object.
Any object to be tracked.
The customer can just make a lot of pictures. I mean, a lot. Make some picture or some video of the object. And then our training module can reconstruct the CAD of the object, can have it in the simulator, and you can interact in real time.
Very nice. So the whole system here, actually, we believe that to enable this concept of human-robot teaming, we need 3 essential elements. One is better sensors, like the ones you are developing. Sensors that are everywhere, not only on board of the robot, but on board of the person and in the environment. So
exactly what's going on.
That's where your system fits in. And then the second element to enable this transition is better motors, better actuators that are compliant and can adapt to these very close levels of teaming. And the last point is better algorithms, better software. So I think that your work fits very well within this aspect. And I would like to ask you, like, as a possible applications, like what is your idea?
So, I mean, sky is the limit for this kind of application for motion capture. So, of course, human-robot collaboration is one of the most promising. This, as we said, it's very important for the robot to know where the human is. But for instance, also in industrial applications, we want to track the ergonomics of people that are working to tell them if they're not carrying out their duties in the most ergonomic way. Because as you know, European Union is spending so much money for musculoskeletal disorders that are coming from this kind of injuries. Every year, 240 billion euros.
So it will affect the budget and the spending.
to recover health and on people that cannot go to work because of things. Then I have written them here. So rehabilitation and health. So maybe if you want your patient to perform some actions and you want to track every joint of the patient. And after some weeks of rehabilitation or after every day, you can ask the patient to perform the same gestures, the same movements, and we can track the progress of the patient in rehabilitation.
Very nice. And in countries like Italy
Yes.
and Norway, where the population is aging, this can have a really big impact.
Yes.
Yeah.
Another vertical is given by sports.
By sport?
Yes. So we've been in contact with also some gyms, personal trainers, sport teams of various sports. And here, what we want to improve is the performance of the athletes. So you want to track if they are doing the movements in the correct way, because when they start doing the same movements that they have been doing for many months, that is the same movements. If you see they start doing the movements a bit wrong, let's say, or a bit
slightly different
way, it means that probably they're getting injured, but you cannot see it with human eyes because maybe it's the change of a few degrees of a joint, maybe especially on the knee, for instance. And so these also are quite promising markets. And the last but not least is the virtual, so VR, AR, mixed reality. So with the headset, we are developing an application in which you can wear the headset and you can see in real time the position of the avatar, as you can see now in the screen. And we can also overimpose it to the person. So we can check while the person is moving with the VR, every joint, what is the angle of every joint, so we can track the performances in real time.
That's also interesting. Like we live in this transition, like from real world to hybrid worlds. So thank you so much, Pietro, for your nice introduction. And we look forward to see the applications coming up.
You want to test our last demo with the robots?
Yeah, sure.
I can let you test. Yes. So if you approach the table, you can show your hands. Yeah. Come closer to so that we have the hand track there.
Yeah.
That finger is tracked. And if you point with your finger to an object, right? Point to an object, and you will see that the robots will go to that object. Yes, you can put your hand down. And in this way, we are showing the ROS integration in the ecosystem and how accurate is also the object detection. Because if you move around the objects, there is no, in that area, yes, exactly. We leave it for demo purposes because we don't want to give anyone from the audience. But you see how accurate it is to track the objects so that the robot can pick up in the exact location what the person is pointing to.
Very nice. It's interesting to see like the accuracy, and the idea is really interesting. This idea of collaborating. I'm teaching the robots what to do, and we are sharing decisions.
Yeah. So we are seeking both for European proposal collaboration, and from June this year, we are starting also to give out the prototype, research center, universities of companies. So I hope someone listening to the podcast can come to us and know better about our prototype and eventually to install it in their labs. So it would be very nice.
Very good, Pietro.
Yes.
It's been a pleasure.
It's a pleasure for us.
See you soon.
Yes. Thank you.
Welcome everyone to this new episode of Among Us, Human Robot Teaming. We are in Vienna for the IEEE ICRA conference, which is the biggest robotics automation conference in the world, the most pioneering one. And I'm extremely happy to have a guest here with me, Erik Ballesteros.
Hey, thanks for having me. It's an absolute pleasure to be here.
When we met through our common friends from Siena, Syed and the others, I immediately saw your spark and your willingness to connect.
Oh, yeah. it's just been a, fantastic, time out here because everyone's just so energetic, so ecstatic, it's just all just good vibes, right?
Good vibes, and really the point of attending such a conference in this fantastic venue.
Oh yeah. I mean, I couldn't be more honored to be here, amongst just such passionate, and talented individuals. Like it really is just a special place. So I'm very happy to say the least.
I immediately noticed the link of your research with the concept of human-robot teaming.
Oh yeah.
And I would like to introduce you a little bit more formally by reading your biography. So Erik is currently a graduate researcher at MIT in mechanical engineering at the laboratory of Albert Loff. And your supervisor is Dr. Ari Asada.
Yep.
So he's very well known, and he has pioneered the concept of grasping, if I remember correctly.
Yeah, that and direct drive robotics. So a lot in the actuation space as well.
Very
yeah.
inspiring. And Erik is also a former hardware quality assurance engineer at the Jet Propulsion Laboratory. And currently you're also affiliated with NASA.
Yes. Yeah. So I'm currently we call it's an NSTGRO fellowship, very long acronym as NASA is very famous for. But it basically sponsors my PhD research all the way up until graduation next year. And before that, I worked at, various positions all over NASA and other parts of the industry for about 8 years, I want to say. So yeah, more of like an engineer first and then happened to get into a research position. And I'm seeing a lot of synergies between the two, halves of that playing field. So yeah, it's been a good time.
Very interesting. And again, I see your passion when you tell about your career and your past involvement. And I was just going to introduce how your research actually connects with the concept of human-robot teaming.
Oh, yeah.
So the idea of human-robot teaming, just to summarize it for our listeners, is this concept of really close collaboration between humans and machines.
Yep.
Where these two entities or multiple entities, maybe a hybrid team, they share physical space.
Yep.
They share forces, maybe lifting a heavy object together.
Mm-hmm.
And they also share decisions.
Yep.
So we used to have in the past the human always in charge, teleoperating or controlling the robots. And now there is this concept of more fluid sharing of autonomy. So for some specific tasks, maybe the human is still in charge. But for some other jobs, maybe the robot has a better experience or more experience, and then we can delegate some of the tasks to the machines.
It makes perfect sense. That's exactly the kind of field and the kind of problems I'm looking at right now. Actually, it's such a fascinating field because there's a lot of nuances, right, between human robotic collaboration and trying to figure out which one takes priority over the other. That is definitely the bleeding edge in this field for sure.
And I was really curious about one nice graphic that I noticed on your website.
Oh yeah,
with the Vitruvian sketch from Da Vinci that you have actually modified. Probably this graphic, in my opinion, captures your research perspective.
Oh yeah.
I'd like to say something more about.
Yeah, of course. So kind of at a glance, very like high level. So my research is I develop a type of wearable robotic system known as supernumerary robotic limbs, or to keep it simple, we call it super limbs. Super limbs. And the best way to think of it from like a pictorial perspective, it's kind of like, you've ever seen the Spider-Man, the comics or the films, it's like Dr. Octopus, the villain.
Very interesting. I think now we are talking about superheroes.
Yeah, quite literally, or supervillains, right? Whichever side you take it on, right? But the whole concept basically is that you have these extra appendages that can be either arms, legs, combination thereof, or just something completely new. And what it does is it can kind of almost reinvent, how we as humans physically interface with the world around us. So now you have this active robotic system sort of in the loop with the human and trying to figure out ways of, integrating, the human robot response in very fluidic ways. And there's a lot of unique challenges with that. And then
so you're augmenting the human capabilities.
Quite literally. Yeah. So a funny thing that usually happens with my research is a lot of times when I present it, people say, oh, it's like an exoskeleton or like a prosthetic. But the key difference is that with like an exoskeleton, for example, they're actuators that are sort of in line with your own body. So they augment your already pre-existing limbs, and then prosthetics just replace lost ones. But this is just completely new appendages. So it creates this interesting paradigm where now you can have effectively an infinite number of use cases or scenarios of how a human could, do a task.
We're talking about the possibility of adding an extra finger, an extra arm, an extra leg.
Exactly. Exactly. And these are all exactly morphologies that a lot of people in this area are actively exploring. So even, today, this week at ICRA, I've been talking with people that are working on augmented tails, extra fingers. Even some of my predecessors in my lab, worked on those exact types of scenarios. So now with me, I'm focused on a much more direct, application, trying to kind of move it past the, research phase and really trying to get it into sort of this adoptable industrial application. And looking at astronauts particularly, there's a lot of interesting, use cases.
Like a perfect application. Right?
Oh yeah. One of the really interesting things with an astronaut application is that NASA, is, with all the, the history, they document, processes very, very intently with a lot of good information about what they expect to do, what they want to, what they want to measure. So you can use this information to sort of evaluate and, and filter out good ideas from bad ones. So it gives us a perfect proving ground to sort of really test this technology and kind of move it from this laboratory space into an actual like deployable system. So that's really where, I, as an engineer, slash researcher, really, find a lot of intrigue, you could say.
You want to push your prototypes to the highest TRL.
Oh yeah, that's
as possible.
Oh yeah, that's definitely the plan.
Like I really like the Vitruvian augmented figure that you have, where you mentioned three key elements:
Yes,
augmentation, expanding the possibilities, I guess, humans, and reinventing.
Exactly.
Like reinventing what, the tasks, or what?
Oh, I think even more philosophical than that. So the idea is, right, you augment a human, right? You sort of redefine how they, can physically adapt themselves. And then you get into the latter parts where you talk about, this idea of like reinvention, right? And the whole point of that is like it reinvents how a human physically interfaces with the world around them. One thing I find really interesting from a very high philosophical level is, especially with recent trends with like AI and humanoids, there's this push, especially with investors and the press, to say, oh, humanoids are just going to outright replace humans, like factories or, where it may be. And I think that's a little facetious, just particularly just because it's like humanoids, yeah, they're being built around, like human subspaces, right? So they can work, in our space. But humanoids at the end of the day, are not able to adapt very well to novel situations or be able to like readily change when something different happens. Yeah, maybe we'll eventually get to that point, but that's not for, much longer. So you need to have a way of sort of kind of integrating humans with robotic systems and sort of creating this next like evolutionary chain in humanity, right? Because evolutionary, right? We're always changing, animals as humans, and as humans, a robotic is just a kind of like a physical extension of our own creativity, right?
That's really, really interesting, and especially in the context of this podcast where we focus on human robot teaming. We're now really talking about a very intimate connection between humans and machines.
Yes.
Even the possibility of evolving as a common hybrid species.
Exactly. And it's interesting because when you start getting into like this whole evolutionary, chain.
So getting better, right?
Getting better.
Millions of years of evolution, we have developed this number of limbs, this number of fingers.
Yeah, exactly.
We were manipulating and interacting with similar objects. We were building objects.
Oh yeah.
Like the shapes and in the size that we can handle, right?
Exactly. And it goes into like, being able to survive, survival instincts. And it's funny because saving energy, us humans, right? When we think about like how we locomote, right? We're really good at running long distances. But maybe not running so fast, but evolutionarily speaking, right? Like humans being these hunters, right? We would chase a mammoth endlessly. They could run very fast, but they can't run very far. Whereas we can just kind of keep going. So it made us very effective hunters, which then eventually led to us, succeeding as a species, right?
And for example, one of the evolutionary key elements that has distinguished humans from the rest of the animals is the opposable thumb, right?
Big time.
Because we can grasp tools. We can
I always think back to that. You ever seen 2001: A Space Odyssey? So it's like the opening theme, right? Where you have all the apes around, and then the one is able to grab the hammer, and it creates that massive, like grandiose, eureka moment, right? Same kind of concept. And now we're in this new age, right? So it's like, where is that next, big, grasping of the hammer, right? So,
Give a huge advantage to humanity if
oh
we
yeah,
integrate and evolve.
exactly. Because now our survival is, with against humanoids and AI, right? So how do you make humans still relevant in this rapidly expanding, space, right? So that's where I kind of come in, is like, this is where, I think humans can have this next evolutionary step, makes us still relevant, if not more capable than anything that could be out there. And it comes with a lot of interesting challenges. So it's just a very, very exciting space to be in.
So what kind of challenges do you foresee? Like, for example, how do you normally uh, build this interface between humans and augmented limbs?
Mm-hmm.
You have a closed loop, right?
Yeah, so we're actively exploring a lot of those areas. So a lot of the research we've been doing now has been in the physical space, like designing and sort of coming up with a methodology to design these types of wearables. Because one of the problems is when you have these these wearable manipulators, the design space is so unconstrained, so difficult to come to a unified, like, this design works. And in robotics, a common trope is you build a robotic system, it's very good at doing one particular thing over and over again. But now with a human in the loop, you have to have so many different capabilities all nestled within each other. So then, so that was a lot what the current research is. And then you talk about, getting the control spaces. What I find interesting, right, is there's these two sort of schools of thought with controls. There's like, wearable sensors, having, like EMGs, or, having like IMUs on you, all these different, like sensory tools, or even like now with science fiction.
So you're monitoring muscle activity, or you're monitoring inertia.
Actually, it's a little bit more external than that, because what we focus on is, so as an engineer, I care very much about, requirements and, and like actual trying to get a system deployed. And the issue with a lot of wearables, like sensors and whatnot, is that you have a lot of noise, a lot of variation in how it's mounted. And that can create a lot of issues when it comes to trying to create very tight, very reliable closed loop control. So I come from the side of looking at things more external, like looking out from the way in. So looking at a human and trying to infer what their intention is, and having the robot have its own internal intention.
For example, this is a very important aspect that we are including in this concept of human-robot teaming, because it's not enough anymore to know what is happening right now.
Yep.
We need to predict
exactly
what's the human intention, what's going to happen.
Oh yeah.
Next time frame, right?
Exactly. Prediction is such a, that's definitely where everything's going. I know in history, right, there's been a lot of reactive control where you have a system, there's some feedback, and with a human, right, they've noticed through a lot of studies that when you have that type of paradigm, the stability of the system or the comfort of the human user is very low, right? It just feels very unnatural working with super limbs in that way. But when you have a predictive element, right, where the robot can anticipate and kind of like almost work with you as you're performing the action, we've noticed, not with my research, with other researchers, that's a very friendly type of approach to creating this like closed loop control, more natural, more realistic, intuitive. So I'm all about trying to minimize the amount of cognitive load on the human, and the robot does its own thing, but it acts completely in the interest of the human, and trying to create sort of like this it's like a second brain, but the brain is completely adaptable to like the main human, right? I use
second unit,
like a partner almost.
Yeah.
I like to use the analogy.
Team member, right?
Exactly. Actually, I use this analogy a lot. You ever watch like old like cop shows in the 80s? So there's this whole idea. There's this very common trope in those shows of like the junior cop and senior cop. You have this one senior cop. He gets a new partner. It's a junior guy, new to the force, doesn't really understand anything yet, but he completely follows the senior cop to a T. Picks up on the mannerisms, learns what to do, what not to do, and then by the end of the the show, this junior cop is effectively like a second, extension of the senior cop, and they're just working flawlessly. It's almost like a second language, an underlying, like theme to them. So I'm trying to create a similar type of, approach with a robot, where the robot is your, your junior cop, and then you as the wearer are the senior cop. And it's just a very symbiotic relationship, and all the controls to figure that out. It's very unique and very interesting. So,
I see a lot of really a lot of analogies, and the framing is really within the topic of this podcast. And my vision is like to enable this concept of HRT. Actually, we need three essential elements that you already touched a little bit. Better sensors, so sensors everywhere, not only on the robots but also on the person, maybe in the environment. Better actuators. Perhaps you are also considering more elastic or hybrid actuation systems that are more safe and compliant. And the third point, you also mentioned, it's prediction algorithms, better algorithms, right? So these three key elements, I think, are also relevant.
Oh, yeah.
For your research.
You're effectively mapping out what, the future is looking like for me. These are all very important areas, especially when it comes to, these super limb systems.
What kind of actuators are you currently using?
So we work with my research right now, we work in close collaboration with the Jet Propulsion Lab, or JPL. And we use these actuators. It's from this program called EELS. It was this large snake-like robot that was supposed to go to Europa, dig itself through the ice sheets to sort of get into the water underneath to do surveying for extraterrestrial life. So what happened was, with my research for the first 2 years of my PhD, I did a very comprehensive design study into evaluating the kinematic structures for these super limbs. And one of my collaborators at JPL said, "Hey, Erik, great news. We have these actuators you could use. They were going to be used for this EELS mission, but kind of with the current state of things, the team isn't around to use them anymore. But we have a lot of spares. Would you be interested?" I was like, "Well, yeah. It's as a graduate student, we don't have this endless budget to work with for actuators. So using these, state of the art, high torque density actuators, it's exactly what we use. So they're called EELS actuators. And they put out, I think, 400 Newton meters of MPT, and they only weigh about 3 to 4 kilograms a unit. So these are like monsters in a little package. Definitely could fold you in half if they wanted to. So there's a whole nother, set of, things we got to figure out with that end, right? But we're using that right now just because it, on an Earth setting, we're trying to do a lot of these like technological demonstrations. They can actually work under Earth gravity. But you allude towards, actuators, right? Soft actuators, different types of mechanisms. When you go into space, right, you want to try to bring the form factor down. So it's not as, there's not as much mass. It's a little bit smaller packaging so astronauts could use it. You have to start talking about these morphologies. So an active area we're looking at is my collaborators are currently looking at new actuator families. That sort of takes this idea of the EELS actuators, but brings down the packaging size, even looks at soft actuation potentially. But of course, there's, drawbacks to even that side. So there's a lot of trade-off studies, I guess, that have to get done. But this is all happening this summer. So yeah, very fun.
I also see some analogies with one of the robots we are designing in my research group.
Oh, yeah?
Which is a snake like robot, which has several degrees of freedom. And so far, we have not considered the possibility of, using it as a extra limb or anything. But
oh, yeah,
it could be used perhaps as a tail or anything else, right?
Oh, yeah. There's using this like continuous type of actuation system, it brings so much unique, like, I guess you could say like augmentation abilities, right? Because when you think about like a classical manipulator, right, with like fixed lengths with these, these joints in the middle, there's only so much you can get away with in terms of like, transferring inertial loads or being able to like, move in certain ways. You're very limited by that, right?
In a way, we have kind of used the concept of augmentation because, for example, we have combined the locomotion with grasping abilities. So, for example, we use the tail of the snake to wrap around an object.
Right. Interesting.
Links are used for locomotion.
Oh, that's really cool.
Yeah.
And it's cool because it's like a very, what's the word? It's a very like out of the box type of application. Like you would never consider that, right? Which is so cool. And especially like in the field of like continuous soft robotics, is like there's so many things that like we have yet to like discover, right? And then to kind of loop it with a lot of the future direction with like AI and like like machine learning. There's a lot of interesting ways with it because we as engineers, we're inherently very we try to be very creative, right? We like to like exploit our creativity and find really new ways of doing whatever we want to do. And robotics is very ripe for that type of application. But now with like AI and a lot of these other types of tools, you can now discover completely novel methods that even you didn't consider and almost creates a synergy, right? So that's so cool that you're able to come up with like a really like, almost like a combined, type of system. blend the two halves of robotics into one system. That's really cool.
Thank you, man. And, so I take the opportunity to invite our viewers and our listeners to have a look on Erik's website. Really good features, really interesting animations. And with this, I would also like to ask Erik. So we have talked about a real clear possible application that is in space operations. Do you see any other possible applications like in everyday life? How this is going to impact people here in everyday life?
So what's really nice about this technology, so a little bit of a story. So about 12 or 13 years ago, my advisor, Harry Sada, sort of presented this concept into the academic community. And he originally pitched it for astronaut applications. At the time, NASA's like, oh, you're crazy, like this is nuts. But this is 12, 13 years ago. So the technology was still kind of, getting figured out. So he took the idea and he kind of pivoted to doing like assistive Medicare, like elder care, even like people who maybe have like mobility issues, and not just that, like industrial workers, people working in factory floors, because there's so many applications here on the Earth that are, in my opinion, like far more important. It's just that space has a very clear defined use case. It's also very fascinating, which can be extrapolated back into Earth. One area that our lab spends a lot of time on is particularly in ergonomics. So I mean, for let's like military, right? So military applications, a lot of soldiers, actually combat's a very small percentage of like what people do in the military. It's mainly a logistics kind of job. So you're carrying boxes around, you're carrying backpacks, very long distance, repeatedly over and over and over again. And as you do that, you get a lot of back pain or leg pain. So a lot of veterans, when they leave the service, reports chronic back pains, and they're going through all this therapy. My older brother, has a herniated disc. And this is very common. So it's like being able to create some sort of system that can help offload some of that mass and be able to sort of prevent you from having to have that issue, is so important. So basically it's a system that kind of like augments you, where it prevents you from having these like horrible debilitating conditions later in life, allows you to live your life to the fullest. So that's
really interesting.
Yeah.
It's like, I would like to conclude this really interesting talk with your vision. You see,
oh man, there's so much.
Probably a challenging point.
Oh no, it's
We
fun.
talked about superheroes.
Yeah.
Here, just the sky is the limit, right?
Oh yeah, like there's a joke, right? Whenever people talk about my research, like, oh my gosh, maybe like next Doc Ock or Doc Evil, like, maybe like. So in terms of future direction, what I can see is this idea that like super limbs becomes almost like a everyday type of tool for people like working in industrial factories or military or even in space. And the whole idea basically is like I envision literally like the next evolutionary chain in humanity. So like right now we're talking.
Imagine now this picture, this famous picture with the evolutionary process that starts with the apes and then
works its way up to humans, and now humans with robots.
Sapiens.
Exactly.
So what's next? Maybe a hybrid.
Exactly, some sort of hybrid, whether it be like extra legs or arms. It'll be very tailored, because what's interesting is thinking about humanity, right? And as we've moved as a society, people are becoming much more specialized, right? Like we're really kind of like locking into like very particular fields, and some people are expanding and trying out different things. But when you have very specialized humans, right, you have to have very specialized morphologies. If we think about it in the physical space, right? So let's think about like technicians, for example, right? A technician working, doing like, turning some bolts, but they're in a weird overhang position. So could they have a particular robotic augment that is tailored to them? So now they're like, it's almost like a specialized human being, right?
This also, if we see this evolutionary idea, like it goes also in line with the idea of augmenting human brains.
Yes.
Neuralink.
Mm-hmm.
So like a way to evolve with augmentation of our brain, maybe our limbs.
Oh yeah.
So it's in line with this trend of.
Absolutely. And it's cool because I know a lot of prior research, they looked at like the whole phantom limb effect, right? So like as you wear these systems, like, so I did a study a few years ago when we first made a concept for the system, where I just, these kinematic structures down to my back. There's no sensors, no like haptic feedback, other than just the interface, right? We did some studies where I was standing up with these, these actuated, kinematic structures. And after doing it for only an hour, I would start feeling like the limbs on my back, and it would felt a part of my body a little bit. There's a lot of studies where people can very quickly kind of morph their brains to like realize there's these additional limbs. So yeah, in terms of like the more like metaphysical side, right? Like people can definitely start to like see themselves with extra limbs, whether it's a tail, whether it's, these extra arms, because the human brain is extra finger, literally anything that's is an extension of your body, right? Because, our brains are so malleable, and that's one of the biggest advantages that we as, a biological species has. In robotics, a lot of, algorithms can do it too, but we have such a deeply nested way of doing it. And there's so much you can use that for, right?
One more point I wanted to discuss with you. What is like in terms of feedback? Since you mentioned now this human capability of adapting, getting used to the extension, what kind of feedback is best, or do you see would be best to give to the human?
Oh man,
is it touch or is a combination of?
But that is a very hotly debated topic. I would say, there's many different modalities you could say, right? So how you do feedback. Haptics seems to be a very popular one because it's the least invasive. There's obviously other ones where you get a little bit more like kind of like into like the actual spinal column and like, kind of exciting different neurons and different groups like that. But of course it comes with a lot of, like
that requires
surgical or just very like intentionally, invasive stuff. So there's pros and cons with everything. It's just a matter of, it really depends on what the application is. For me personally, so I come from I'm an engineer, by trade. So I come at it as a sort of like what's the word? Like very, like what is the most realistic, like forward application. So it's minimizing it, right? So haptics probably the closest, I would say. It's, something that doesn't really
less invasive and
less invasive, can be taken out. It can be modified. And, and of course there's issues with it, right? The resolution that you get is a little kind of foreboding. But at the same time, if you're really smart about how you use it, you could more practical. That's the word. It's the idea that like you can be really smart with how you use the haptics and with how, algorithms and how we do control is becoming more and more sophisticated and more intelligent. You can get away with very little information. My goal is to try to take such little information about the human and get a ton of information out of it. That's kind of, and actually, my advisor, that's like the core, the heart of his research from day one. So trying to, figure out an application where we can really exploit and like really dig into that, that idea is exactly what we're looking at now, take very little information and get a whole plethora of, data out of it.
Really inspiring. So I really enjoyed this chat with you, Erik. We have started from the Vitruvian sketch from Da Vinci, and we have then moved into the concept of evolution for humanity, and we went into space. And I think this is really, really visionary research that you are working on.
Thank you.
It's been a pleasure to have you here as a guest.
Likewise, Filippo. This has been so cool to be able to talk to you about this. Like I love this stuff. Like hearing about all the cool work out here. Like it's just, literally growing up, I always loved building with Lego bricks and all that. And now it's like, hey, here we are, right? It's cool to see how everything kind of just comes full circle. It's the best.
Very, very cool. And of course, one of the aim of this podcast is to connect. So our listeners, our viewers, feel free to reach out. We will add all the links to our to the podcast description. And I look forward to see your augmented limbs in space. Pretty soon.
It's only a matter of time. There's still a lot to figure out. Oh man, if we work with NASA, the bureaucracy and everything, but hopefully soon. Hopefully soon if we play the cards right? So, but that's the plan.
Thank you, Erik. And
thank you, Philly.
See you to the next episode.
Thank you very much.
Welcome everyone to this new episode of Among Us, human robot teaming. And today it's a pleasure to have a very interesting guest, Kentaro Barhait. He's a PhD fellow at the MIT Institute, and his advisor is Professor Hari Asada. It's very nice to meet you. We are at ICRA 2026 in Vienna, and we actually met casually we were attending the gala dinner yesterday evening, and we immediately connected. You were so friendly, and you were showing me your research activity, and something that is really, it means a lot for me personally. Your research is about grasping. Would you like to say something to our guests?
Yeah, thank you so much for having me on. I'm really excited. It was great meeting you, and your work is really exciting as well. I'm glad to be able to chat about it. It was cool up.
Yeah, and Kentaro is actually working on something really cool and new, which is about full closure grasping.
Full closure grasping.
Yeah. So how does this frame? How can we frame this into the concept of human-robot teaming? In my opinion, I think that this alternative way of grasping is really relevant when we consider this really close interaction between humans and machines. And as I like to say, to enable the transition from the previous way of building human-robot collaboration, to enable this transition to human-robot teaming, I believe that we need three essential elements. We need better actuators, actuators that are more intrinsically safe when we possibly have some unintentional collision between humans and machines. We need better sensors so that the machines can be much more aware of what is happening, and also we should be able to do predictions. It's not enough anymore to know what is happening right now, but we need to have a time frame to dynamically adapt to the situation. And then the third point is better software, better algorithms, which is today are kind of enabled by this wave of the artificial intelligence, right?
Yes. Yeah.
So I think that your work within full closure grasping could be framed within the concept of building better actuation systems and also to enable this interface, this safe interface between humans and machines.
Absolutely.
Would you like to show us a little bit more about your work?
Yeah, absolutely. So to summarize loop closure grasping, the concept fundamentally is about utilizing topological transformations between the grasping mechanism's morphology from open loop to closed loop to enable simultaneously strong, gentle, and versatile grasp. And
these three keywords are really relevant, right? Because it's very difficult to find the balance in between, right?
Right. These properties that are usually conflicting, and yet they're still very important for many important high impact applications. So, generally open loop mechanisms, which are these mechanisms that start from the base, go over some length, and end on a tip. Fingers and almost all grasping mechanisms today are open loop. And they're very useful for creating versatile grasps. And so you can move the tips around freely in space. They're not constrained to position them and create the graph that you want for whatever object, environment, configuration that you have passed. But there is a limitation in the ability to handle heavy yet fragile objects. And so these are objects that weigh significantly more or, require high forces relative to the safe forces that they can take without damage. A great example of this is the human body. We weigh a lot, and to lift them, it requires a lot of force. But if you just arbitrarily apply that force onto a person, that can be counterproductive. And the way that this is addressed in industry for millennia is using things like straps and slings. So, in elder care, patient care, search and rescue, agriculture, even in heavy industry, they're very beneficial for handling these heavy fragile objects because the load is born in the tension of the mechanism, not in the bending stiffness. And so as opposed to with open loop mechanisms, you require more bending stiffness to bear the higher loads, and that higher stiffness kind of is in contrast to the client interaction that can create safe interaction. Whereas closed loop mechanisms, they bear the load and tension and thus don't require any bending stiffness and are able to then just naturally conform to the shape of the object. And
so like our fingers are actually open loop,
yes,
right?
Yes, our fingers are open loop, and then closed loop is like straps and slings, where you take, if you imagine, you go from the base, go over some length, and say you like welded the tips of my fingers together. It doesn't end at a tip; it comes back to the base, and that's how you close the loop. And that's what allows the load to be borne in tension as opposed to dependent. But at the same time, if the loop is closed, you have to somehow get the object inside the loop, right? It's more limited than open loop mechanisms for grasp versatility, which is really important for autonomous deployable robotics. And so what we do is we present this paradigm of grasping that transitions the mechanism from the open loop topology to closed by first wrapping, and maybe I could show
Please.
So just to present a visual.
So what do we have here? We have a robotic manipulator. He's going to grasp a watermelon.
Yes, exactly. So that in this case, we use a mechanism called vine robots, these soft-growing robots, as our grasping mechanism. And it starts off as an open loop where it navigates its tip around the object, and it can do so freely because its tip is free as an open loop, and then brings its tip back to the base, at which point it's fastened, and it closes the loop to then lift them with the mechanism tension. And so you get then both the benefits of that, the open loop versatility. You can see actually here, a wide range of graphs that we're able to achieve. And then also once you close the loop, you can handle these heavy yet fragile objects because of that topology.
Very nice. I like, for example, this video is very relevant. It's already triggering me some possible applications like search and rescue operations. And the one you had the segment with lifting a human.
Yes.
So applications within healthcare, for example, yeah?
Yes. Yeah. Many important applications. So, this space of heavy yet fragile objects is something that robotics hasn't really explored a lot. And just because of these previous contradictions and, using these traditional paradigms of grasping that almost always, not all, but almost always use these open loop mechanisms. And I can go back to a visual of, there we go. And but just because it hasn't been explored as much doesn't mean that there's not really important applications, such as handling seniors could be enormous. So healthcare, elder care with aging populations, the need to take care of people who are physically less able, and with declining young population to take care of them, being able to assist the current workforce to handle the aging population, very important. Same goes with people with physical disabilities, just in hospitals. Search and rescue is another very important one, for being able to not just find, but also grab and rescue the people in the field. And then, it's not just for humans as well. So any object that has that high force requirement to handle them relative to the forces they can take. So another example would be like port automation. So say you are lifting a ship from one side of a canal to another, or maybe not a canal, but just moving these very heavy payloads. When you think of a ship, you usually don't think it's fragile, right? It's a very strong, sturdy metal structure. But relative to the weight that it is fragile because just so much force is required to lift it. And so things like port automation, heavy industry manufacturing.
So for example, I was thinking before, like, about the possibility of using this system also for assembly or disassembly tasks, where you can kind of balance the workload between humans and machines, right? You can delegate the most heavy and stressful tasks to the machine, while the humans can take care of more dexterous manipulation tasks.
Absolutely. Yeah. Yeah. Because that's another aspect of these heavy yet fragile objects are a space of applications that are not reachable by humans on their own. You know, like we can't lift a ship, right? But humans are still obviously very good at those smaller scale dexterous tasks that are needed, and these applications require the whole scope of these different tasks, both the handling of these large payloads as well as the dexterous assembly, manipulation, fastening, stuff like that. So
this is for the concept of human-robot teaming is very interesting because we can have some level of fluidity where you can shift workload from humans to machines, and you can also balance the autonomy. Like you can have different levels of autonomy according to the task that you are performing. So sometimes it could be that the human is in charge of a specific task because the human has accumulated knowledge and has better dexterous capabilities and so on. While sometimes for a specific task, everything is delegated. It's the machine in charge.
Right.
So taking the heavy objects and perhaps performing tasks that can be delegated.
Right.
Yeah.
Absolutely. Yeah. I think that the capabilities of the human and the robot complement each other very well. It's not replacing
That's exactly the point, right? With
Exactly.
the human-robot teaming, we don't want to replace humans. We want to work as a team.
Right.
Yeah.
Right. Yeah. I can give the example of some other. Yeah. So
Please.
I think a really good example of this is, we presented this paper on weak closure grasping, kind of an offshoot work. Oh, and I should also state that this work, the past few works that have been done on weak closure grasping and also the work I'll show now, was co-led a collaboration between my group at MIT, with Ari Shaba, and Alison Okamu's group at Stanford, and her student Godson Osip. So we were co-first authors on all the these papers. So,
Cool.
all credit to that as well. And so another paper that we, wrote and presented was this growing sling. So it's this vine robot. So these are these inflated tubes that grow from the tip via an inversion mechanism. It's this mechanism that is, seen a lot in the vine robot literature, but in our case, it's cross-section is programmed to be flat. And the reason we did this was to enable, actually, maybe I'll show the larger video over here, is to enable automatic placing of a sling underneath a patient. And, this process of placing the sling underneath humans is the most laborious and strenuous part for caregivers and nurses to do physically. It requires to safely do it. It requires multiple caregivers, and because of that, this task of transferring humans is often not done to the rate that would be needed for these patients to have the quality of life that they would want. And so by automating this process, I'll go back. There we go. Actually, this is also building a little bit on previous work that was done from growing sling as well. We just kind of take a different approach. But you can see in this video that a nurse is still required. You still need to be able to attach the sling to a Hoyer lift. You need to be able to interact personally with the patient. And you need to be able to make sure it's all going safe, it's all going properly. So the physical burden of maneuvering the person and lifting that is then taken away from them. But the dexterous manipulations and that interpersonal interaction is still entirely necessary. And so I think this is another example of, we can complement the capabilities of the human workers through that human robot teaming.
Very good.
Not replace.
Yeah, I think that's a very interesting term that you have used, augmenting capabilities and through the teaming concept. Very interesting.
Yeah.
And previously I said that the topic of grasping is really, I'm very passionate about this topic because of my previous research. And I see some analogies, for example, with the design of manipulators that have many degrees of freedom.
Right.
Like in your case, you have ideally an infinite number of degrees of freedom. And from a control perspective, that's also very interesting.
It is. Yeah. Yeah, absolutely. It's yes. So like you said, ideally, infinite would be the extreme we would like to go to, and in this case, that's what we're doing with the vine robots and loop closure grasping. But in cases, infinite may not be necessary. It really just comes down to the pressure distribution you're able to achieve with the segments that are interacting with the body. So you're
I was showing some previous work about design of modular grippers, where you basically use this idea of modularity to increasingly add modules and fingers, and then you can come up with designs that are almost unexpected. Like for complex shapes, you have, like, for example, 3 fingers that look like almost like a snake robot.
Right.
And this also connects me to some previous research that we have done building, actually designing snake robots, where we have this idea of multiple joints connected together. And I see some analogies with your work.
Absolutely. Yeah.
And when we were designing this kind of robots, also we realized that it's important to have to sensorize them.
Right.
What about your perspective on this?
Yeah. So it's very important. Yes. So in the scope of the work that our Dodson, Allison, Stanford collaborators and I have done with this work, really focus on the design. But for autonomous deployable robotics, absolutely, you need that sensitization, that control, and going forward, hopefully, yes, we aim to implement that in a way that we can not only achieve the physical requirements for these heavy yet fragile objects, but also things like detecting the object, understanding what kind of grasp configuration is needed to stably and safely grasp and lift them. Of course, for humans, that's going to be extremely important. Humans vary widely in their, shape, size, the disability or condition that they might have different requirements for how they're handled. And being able to perceive, the state of the human, the state of the environment that they're in. Are they in a chair? Are they in bed? And how can we navigate these line robots around them in such a way that we can robustly handle them is very important. And also, not just for these hospital examples that I keep mentioning, but also search and rescue, field deployments. In cases, you had a great picture here of in rubble. It's a very important and challenging problem that we absolutely should be addressed to make this deployable and useful for robotic apps.
And currently your system is actuated with compressed air, right?
Yes.
So maybe it could be a possibility to use this almost like as a pressure sensor, right? Maybe to read the pressure and estimate the forces.
Absolutely, yeah. That could be one for sure. Yeah. There are some works that use pressure sensing as a form of feedback, so you can estimate the loads, not just of the growing, but also the bending, which is current and future work that we're working on now. To enable that feedback. There are other methods as well. Using things like flex sensors, optical waveguides. There's some great work out of Queen Mary University that focuses on that. I think that's a lot of promise. There are many methods. Computer vision as
Computer
well.
vision, yeah. Nice. And I was looking at one short section of your video where basically your gripper was going horizontally instead of going from the top.
Yes.
So when it goes horizontally, it reminds me even more of a snake, right? You probably can show that clip there.
pull up here.
Yes, this one, yeah.
Yeah.
So here it reminds me a lot of a snake going around, wrapping around the objects. And so it's almost like combining locomotion and grasping. Like we recently did it with the snake robot. So we use the tail of the snake to wrap around the object, and then the remaining part of the snake is used to locomote.
Right. Yeah, absolutely. I see the connections as well. Yeah. I think the way that you're doing it is really interesting because, not only, in our case, we're able to kind of locomote and grow in, around a longer range environment. That's what's kind of the purpose of this video, showing over a long range. We can grasp and pull something. But ultimately, in our case, which, this could be also great for future work, but this is also tethered to the base as well. As opposed to your snake robot is, the entirety of it is locomoting around in the space. So, having that for field applications, having that range of navigation, it's very, very exciting to be able to combine those.
Nice. So I'm really happy to see several analogies and links between our research and with this, I would like to, together with you, maybe to look at the future. What do you see as current challenges, but also the future potential of this kind of systems?
Yeah. So I believe the future is a lot of ripe applications and tasks to address in this area of heavy fragile objects. Like I was saying, this is an area that a lot of robotics has not explored a lot. So many of these existing paradigms use maybe anthropomorphic or these human scale grippers that use these open loop mechanisms. But there's so many important applications that we've been talking about that are involved heavy fragile objects, and I believe kind of unlocking that new area of applications, I think, could be fantastic for expanding the applicability of robotics technology for really important, current day problems and applications. So I think the continuation of loop closure grasping, which, by the way, I at a little bit of a tangent. Internally, we've been calling it TLC, so topological loop closure grasping, because it's about changing the topology. And also TLC, this name goes credit to Dotson Taylor. He came up with it. It's fantastic.
Cool.
TLC is a cheap name that we call it. So the development of TLC, development of loop closure grasping, is in that direction of these heavy yet fragile objects. So understanding more of how can we explain the change of mechanics, the change of the morphology, to further the ability to not just lift the object, but do it so robustly, do it in a reliable way, understanding the fundamental mechanics, the theory of how do we predict the graphs that we need to create. Again, a lot of these heavy fragile objects are very important, very delicate, so that reliability is going to be very important. And then also expanding not just on the theoretical side of the mechanics, but also the technological side of improving the versatility that we're able to create different graph configurations. So, for example, in the scope of this work that we published in Science Advances, the trajectory of the vine robots was determined almost entirely either through preforming the shape of the vine robot, so mechanically designing
pre-shape.
Exactly. Yes. Or using environmental interactions to guide its tip towards the base. And, that was fantastic for the demos that we showed here. There's a certain level of reliability we're able to achieve with that, but to progress that even further, adding things like bending action, which exists in vine robot literature, pneumatic artificial muscles. There's some really great work out of UC San Diego, Tadano Morimoto's group that's doing LCE actuators, tendons. There's many others as well. That I think would be a really great way to make this more versatile to the point where, the long-term vision that I hope for is you imagine like a hand that is able to grow the fingers, wrap around objects, kind of like a vine.
That's very visionary.
Yeah.
I think maybe Pixar is going to make a movie about that.
Yeah. I think that'd be so cool to be able to get that that level of dexterity plus the strength and the depth. I think there's a lot of exciting.
Wait, it's like a new superhero.
Yeah. I think there is a superhero. I'm not too familiar, but it's like this IV superhero, maybe in the Batman. I'm not sure.
Cool.
Yeah, exciting stuff.
Yeah, very exciting. And Kentaro, I really enjoyed our chat, and I look forward to see your research progressing, and also looking forward to connect and collaborate. And as always, we are teaming also between researchers.
Yes.
So human to human teaming.
I'm very, very glad to collaborate. Looking forward to it, and I'm very glad to be in this research community where we can all be a team and progress.
Yeah, I immediately when we met yesterday, I immediately saw your motivation and willingness to open up and collaborate, and I think this is the spark that research needs. So looking forward to the next steps, and with this I would like to say goodbye to our listeners. Would you like to say something?
Thank you for listening, and check out our work, and
we will add all the links to the description, and remember that we are Among Us, and we are human robot teaming. Listen to our ending song, where some of the words will reverberate with what we just discussed. So we are at the booth of Pole Robotics at ICRA 2026 in Vienna, and I have the pleasure to meet one of my friends, Francesco Ferro, who is the head of Eurobotics.
I'm president
of Eurobotics.
CEO and owner of PAL Robotics. Yeah.
So it's a real honor to have you here in this special episode of Among Us, human-robot teaming. And
it's a pleasure for me too. Yeah.
Really a pleasure. It's been a while. We were planning to have this brief chat. Finally, I caught you.
So just speaking about teaming, because this is a very interesting question, and what we are doing now is about collaboration. So especially in robotics, what we are doing here in ICRA is a statement of robotics. So we have a kind of call of action in order to just move the big player in Europe in order to start doing better robots, better application, using AI in our robots, focusing on the real needs in Europe. And this is impossible to do without forming the right team, even also between the different researchers, especially in robotics. We are very good to just mix industry with research, and the idea is to create the best team, say the dream team, in order to make these kind of things happen.
So this is a very fascinating point. So you are teaming up industry with research. You're teaming up different players in the European ecosystem.
Correct.
And so like humans to humans, teaming.
And humans robots.
And human to robots. Yeah.
So this is the idea. But a part of human and human robots, there's also robots human. So the idea is also to have this kind of platform that could be a kind of human and robots, like now here, for example, we have the kind of robots and other with mobile basis and only a single arm that could collaborate between robots and with humans. So we had, for example, Car Robotics, we had a project, it was called Co for Robots, where the collaboration, human, robot, human, and robot, it was a must. So in a different industry now, we are working in different pilot where kind of robots, independently of the form, can just collaborate with other robots.
So hybrid teams, like different morphology of the robots and different specialized tasks.
And interoperability is also nice because it has to be also with different brand. Okay, so if you are purchasing one Tiago for us, has to work with another platform for another provider independently. So for this reason, we are using the de facto standard middleware that is ROS 2 now,
The robotic operating system.
operating system that allow us to mainly for three things. From one side, having this kind of middleware where everybody can just program it. The other side is collaborating with other brands in order to have topics that could just make things sharing the knowledge, let's say in this way. And from the other side, provide for a company that are using this platform a kind of the open source behavior. You can just give it the idea that if tomorrow you want to change provider, you can do in a safe way because you have all the code that is necessary to compile your application.
So this is very, very, very important, and it's also very fascinating to see that you're doing this with that kind of vision, open, and so you talked about teaming, you talked about open standards, and also open architecture, so that this, I think, is going to be really needed, and it's going to drive the European European market and gives possibly a way to compete with other markets.
There are different, let me say, sector that is important to have sovereignty. For example, today, European Commission will just take out the tech sovereignty things. So I didn't read yet, but I will do. And tomorrow in a panel here in the ICRA, we organized with our robotics a very interesting discussion between Osama Khatib, that we represented the global community of robotics, and then other two players from the US and from China, where we can share the vision and try to see how we can collaborate in the different side. And from European side, we need also to have not only collaboration with abroad. For example, now we have foreseen more and more robots from Chinese company, for example, and more intelligence from US company, but also we can have internally for determinate sovereignty, for the sovereignty reason, how we can collaborate with different companies, universities in South Europe to have a similar solution that can allow us to have our sovereignty intact.
Very nice. This is important. With this political asset of the world, it's really needed. And if we go a little bit more on the technical perspective, would you like to tell us a little bit more about
the camera?
Yes.
I don't know if
what.
Yeah, I already asked my colleague. But the robots here, you can see one of the important things is has no head. So without the head, actually, the idea is if you are using this kind of robots for manufacturing or logistics, you don't need to have a head. So having the camera here in front, back, allow two different things. On one side, you can pass goods from one side to the others. Yes, you can also, without a front or back, taking the things instead of in the front on the back, and from the other side, also have a less problem in case of falling down. That is also from our human design. Neck is one of the problems. So when
it's a fragile.
Yeah, we did since 20 years a lot of robots, and so it's the fragile point of human and robots. So without the neck, you can avoid this kind of behavior, and you can continue using the platform without this kind of things. So the robot now, we have a very strong model robots using the whole body control. And recently we also had a lot of work in reinforcement learning and imitation learning. So we have now here in the ICRA the possibility to have the robot jumping and moving with reinforcement learning. And so I can ask also to have this kind of to my colleagues.
Nice. Yeah, we can have a demo so that we can show how it works.
Syed, my colleague, is super nice. He can show the robot jumping.
We are recording in a very crowded environment with 8,000 participants. So it's again, thank you for the time that you have dedicated to us.
Yeah.
We can have a look of the demo.
You see that break? Yeah. Idea. just
And also the particular design of the legs. It's a linear motor.
allowed to have a better precision.
And also stronger legs, right?
Stronger legs, everything that we just concentrated in this part. So you don't have no motors, no electronics in the lower part.
So the inertia is.
And now, yeah.
So we are going to see how it jumps. I see. So thank you very much, Francesco, for the time that you have dedicated to us.
Yeah.
And if you would like to say something to our viewers and listeners.
Yeah. A part of the kangaroo, we have also, still jump. We have also teleportation system in order to do the things. But with the Tiago Pro, we have a new arm that we are just now having the
compliant
compliance inside. So we have the force feedback. Now we have a stable where the robot is right in always in the same place. The things and but most important message to the community is that we need to have passion in order to do these kind of things and do it together between Norway, Spain, Italy, France, wherever country in Europe in order to maintain the strong ecosystem that we have in a very team intercultural. So
thank you very much.
Filippo. Thanks.
among us, not alone in innovation. Shared control, shared creation, rewriting our design. Human robot teaming. Human robot teaming. Through the noise of doubt and distance, through the fear of what may be, we found trust in every motion, in shared autonomy. Not replacement, not surrender, but a fusion of design. Intelligence extended, your decision joined with mine.